Welcome back, and here is lesson 4, which is where we get deep into the weeds of exactly what is going on when we are training a neural network. And we started looking at this in the previous lesson. We were looking at stochastic gradient descent. And so to remind you, we were looking at what Arthur Samuel said. Suppose we arrange for some automatic means of testing the effectiveness of any current weight assignment, or we would call it parameter assignment, in terms of actual performance, and provide a mechanism for altering the weight assignment so as to maximize that performance. So we could make that entirely automatic, and a machine so programmed would learn from its experience. And that was our goal. So our initial attempt on the MNIST dataset was not really based on that. We didn't really have any parameters. So then last week, we tried to figure out how we could parameterize it, how we could create a function that had parameters. And what we thought we could do would be to have something where, the probability of being some particular number was expressed in terms of the pixels of that number and some weights, and then we would just multiply them together and add them up. So we looked at how stochastic gradient descent worked last week, and the basic idea is that we start out by initializing the parameters randomly. We use them to make a prediction using a function such as this one. We then see how good that prediction is by measuring using a loss function. We then calculate the gradient, which is how much would the loss change if I changed one parameter by a little bit. We then use that to make a small step to change each of the parameters by a little bit by multiplying the learning rate by the gradient to get a new set of predictions. And so we went round and round and round a few times until eventually we decided to stop. And so these are the basic 7 steps that we went through. And so we did that for simple quadratic equation. And we had something which looked like this. And so by the end, we had this nice example of a curve getting closer and closer and closer. So I have a little summary at the start of this section, summarizing gradient descent, that Silva and I have in the notebooks in the book of what we just did. So you can review that and make sure it makes sense to you. So now let's use this to create our MNIST 3s versus 7s model. And so to create a model, we're going to need to create something that we can pass into a function like, let's see where it was. Pass into a function like this one. So we need just some pixels that are all lined up and some parameters that are all lined up, and then we're going to sum them up. So our x's are going to be pixels. And so in this case, because we're just going to multiply each pixel by a parameter and add them up, the fact that they're laid out in a grid is not important. So let's reshape those grids and turn them into vectors. The way we reshape things in PyTorch is by using the view method. And so the view method, you can pass to it how large you want each dimension to be. And so in this case, we want the number of columns to be equal to the total number of pixels in each picture, which is 28 times 28, because they're 28 by 28 images. And then the number of rows will be however many rows there are in the data. And so if you just use -1 when you call view, that means, as many as there are in the data. So this will create something of the same with the same total number of elements that we had before. So we can grab all our 3s, we can concatenate them, torch.cat, with all of our 7s, and then reshape that into a matrix where each row is one image with all of the rows and columns of the image all lined up into a single vector. So then we're going to need labels. So that's our x. So we're going to need labels. Our labels will be a 1 for each of the 3s and a 0 for each of the 7s. So basically we're going to create an is3 model. So that's going to create a vector. We actually need it to be a matrix in PyTorch. So unsqueeze will add an additional unit dimension to wherever I've asked for. So here in position 1. So in other words, this is going to turn it from something which is a vector of 12,396 long into a matrix with 12,396 rows and 1 column. That's just what PyTorch expects to see. So now we're going to turn our x and y into a data set. And a data set is a very specific concept in PyTorch. It's something which we can index into using square brackets. And when we do so, it's expected to return a tuple. So here, if we look at, we're going to create this data set, and when we index into it, it's going to return a tuple containing our independent variable and our dependent variable for a particular row. And so to do that, we can use the Python zip function, which takes one element of the first thing and concatenates it with one element of the second thing, and then it does that again and again and again. And so then if we create a list of those, it gives us a data set. It gives us a list, which when we index into it, it's going to contain one image and one label. And so here you can see y, there's my label, and my image. I won't print out the whole thing, but it's a 784 long vector. So that's a really important concept. A data set is something that you can index into and get back a tuple. And here I am, this is called destructuring the tuple, which means I'm taking the two parts of the tuple and putting the first part in one variable and the second part in the other variable, which is something we do a lot in Python. It's pretty handy. A lot of other languages support that as well. Repeat the same 3 steps for our validation set. So we've now got a training data set and a validation data set. Right, so now we need to initialize our parameters. And so to do that, as we've discussed, we just do it randomly. So here's a function that, given some size, some shape, if you like, will randomly initialize using a normal random number distribution in PyTorch. That's what randn does, and we can hit Shift-Tab to see how that works. Okay. And it says here that it's going to have a variance of 1. So I probably shouldn't have called this standard deviation. I probably should have called this variance, actually. So multiply it by the variance to change its variance to whatever is requested, which will default to 1. And then, as we talked about when it comes to calculating our gradients, we have to tell PyTorch which things we want gradients for. And the way we do that is requires grad underscore. Remember, this underscore at the end is a special magic symbol which tells PyTorch that we want this function to actually change the thing that it's referring to. So this will change this tensor such that it requires gradients. So here's some weights. So our weights are going to need to be 28 by 28 by 1 shape. 28 by 28 because every pixel is going to need a weight. And then 1 because we're going to need, again, we're going to need to have that unit access to make it into a column. So that's what PyTorch expects. So there's our weights. Now, just weights by pixels actually isn't going to be enough, because weights by pixels will always equal 0 when the pixels are equal to 0. So it has a 0 intercept. So we really want something where it's like wx plus b, a line. So the b is, we call the bias. And so that's just going to be a single number. So let's grab a single number for our bias. So Remember I told you there's a difference between the parameters and weights, sexually speaking. So here the weights are the W in this equation, the bias is B in this equation, and the weights and bias together is the parameters of the function. They're all the things that we're going to change. They're all the things that have gradients that we're going to update. So there's an important bit of jargon for you. The weights and biases of the model are the parameters. So we can, yes, question.
What's the difference between gradient descent and stochastic gradient descent?
So far we've only done gradient descent. We'll be doing stochastic gradient descent in a few minutes. So we can now create a calculated prediction for one image. So we can take an image such as the first one and multiply by the weights. We'll need to transpose them to make them line up in terms of the rows and columns, and add it up and add the bias, and there is a prediction. We want to do that for every image. We could do that with a for loop, and that would be really, really slow. It wouldn't run on the GPU, and it wouldn't run in optimized C code. So we actually want to use always to do kind of like looping over pixels, looping over images. You always need to try to make sure you're doing that without a Python for loop. In this case, doing this calculation for lots of rows and columns is a mathematical operation called matrix multiply. So if you've forgotten your matrix multiplication, or maybe never quite got around to it at high school, it would be a good idea to have a look at Khan Academy or something to learn about what it is. But it's actually, I'll give you the quick answer. This is from Wikipedia. If these are two matrices A and B, then this element here, 1, 2, in the output is going to be equal to the first bit here times the first bit here plus the second bit here times the second bit here. So it's going to be B12 times A11 plus B22 times A12. That's, you can see the orange matches the orange. Ditto for over here. This would be equal to B13 times A31 plus B23 times A32, and so forth for every part. Here's a great picture of that in action. If you look at matrixmultiplication.xyz, another way to think of it is we can kind of flip the second bit over on top and then multiply each bit together and add them up. Multiply each bit together and add them up. And you can see always the second one here ends up in the second spot and the first one ends up in the first spot. And that's what matrix multiplication is. So we can do our multiply and add up by using matrix multiplication. And in Python, and therefore PyTorch, matrix multiplication is the @ sign operator. So when you see @ that means matrix multiply. So here is our 20.2336. So if I do a matrix multiply of our training set by our weights, and then we add the bias, then here is our 20.336 for the first one. And you can see, though, it's doing every single one. Okay. So that's really important, is that matrix multiplication gives us an optimized way to do these simple linear functions for as many kind of rows and columns as we want. So this is one of the two fundamental equations of any neural network. Some rows of data, rows and columns of data, matrix multiply, some weights, add some bias. And the second one, which we'll see in a moment, is an activation function. So that is some predictions from our randomly initialized model. So we can check how good our model is. And so to do that, we can decide that anything greater than 0, we will call a 3. And anything less than 0, we will call a 7. So preds greater than 0 tells us whether or not something is predicted to be a 3 or not. Then turn that into a float. So rather than true and false, make it 1 and 0, because that's what our training set contains. and then check whether our thresholded predictions are equal to our training set. And this will return true every time a row is correctly predicted and false otherwise. So if we take all those trues and falses and turn them into floats, so that'll be ones and zeros, and then take their mean, it's 0.49. So not surprisingly, our randomly initialized model is right about half the time at predicting 3s from 7s. I added one more method here, which is .item. Without .item, this would return a tensor. It's a rank 0 tensor. It has no rows, it has no columns, it's just a number on its own. But I actually wanted to unwrap it to create a normal Python scalar, mainly just because I wanted to easily see the full set of decimal places. And the reason for that is I want to show you how we're going to calculate the derivative on the accuracy by changing a parameter by a tiny bit. So let's take one parameter, which will be weight 0, and multiply it by 1.0001. And so that's going to make it a little bit bigger. And then if I calculate how the accuracy changes based on the change in that weight, that will be the gradient of the accuracy with respect to that parameter. So I can do that by calculating my new set of predictions, and then I can threshold them, and then I can check whether they're equal to the training set, and then take the mean, and I get back exactly the same number. So remember that gradient is equal to rise over run. If you remember back to your calculus, or if you'd forgotten your calculus, hopefully you've reviewed it on Khan Academy. The change in the y, so y new minus y old, which is 0.4912, etc., minus 0.4912, etc., which is 0, divided by this change, will give us 0. So at this point we have a problem. Our derivative is 0, so we have 0 gradients, which means our step will be 0, which means our prediction will be unchanged. Okay, so we have a problem, and our problem is that our gradient is 0, and with a gradient of 0 we can't take a step and we can't get better predictions. And so intuitively speaking, the reason that our gradient is 0 is because when we change a single pixel by a tiny bit, we might not ever in any way change an actual prediction to change from a 3, predicting a 3, to a 7, or vice versa, because we have this threshold. Okay, and so in other words, our accuracy loss function here is very bumpy. It's like flat step, flat step, flat step. So it's got this 0 gradient all over the place. So what we need to do is use something other than accuracy as our loss function. So let's try and create a new function. And what this new function is going to do is it's going to give us a better value, kind of in much the same way that accuracy gives a better value. So this is the loss. Remember, a small loss is better. So it'll give us a lower loss when the accuracy is better, but it won't have a 0 gradient. So it means that a slightly better prediction needs to have a slightly better loss. So let's have a look at an example. Let's say our targets, our labels of like the is3. Oh, there's just 3 rows, 3 images here. 1, 0, 1. Okay, and we've made some predictions from a neural net, and those predictions gave us 0.9, 0.4, 0.2. So now consider this loss function. Our loss function, we're going to use torch.where, which is basically the same as this list comprehension. It's basically an if statement. So it's going to say for where target equals 1, we're going to return 1 minus predictions. So here target is 1, so it'll be 1 minus 0.9. And where target is not 1, it'll just be predictions. So for these examples here, the first one, target equals 1, will be 1 minus 0.9, which is 0.1. The next one is target equals 0, so it'll just be the prediction, which is 0.4. And then for the third one, it's a 1 for target, so it'll be 1 minus prediction, which is 0.8. And so you can see here, when the prediction is correct, in other words, it's a number, it's a high number when the target is 1, and a low number when the target is 0, these numbers are going to be smaller. So the worst one is when we predicted 0.2, so we really thought that was actually a 0, but it's actually a 1. So we ended up with a 0.8 here, because this is 1 minus prediction, 1 minus 0.2 is 0.8. So we can then take the mean of all of these to calculate a loss. So if you think about it, this loss will be the smallest if the predictions are exactly right. So if we did predictions is actually identical to the targets, then this will be 0, 0, 0. Okay? Whereas if they were exactly wrong, so say they were 1 minus, then it's 1, 1, 1. So it's going to be, the loss will be better, i.e. smaller, when the predictions are closer to the targets. And so here we can now take the mean, and when we do, we get here 0.433. So let's say we change this last bad one, this inaccurate prediction, from 0.2 to 0.8, then the loss gets better from 0.43 to 0.23. So this is just this function, this torch.where.mean. So this is actually pretty good. This is actually a loss function which pretty closely tracks accuracy. As the accuracy is better, the loss will be smaller. But also it doesn't have these zero gradients, because every time we change the prediction, the loss changes because the prediction is literally part of the loss. That's pretty neat, isn't it? One problem is this is only going to work well as long as the predictions are between 0 and 1. Otherwise, this 1 minus prediction thing is going to look a bit funny. So we should try and find a way to ensure that the predictions are always between 0 and 1. And that's also going to just make a lot more intuitive sense, because we like to be able to kind of think of these as if they're like probabilities, or at least nicely scaled numbers. So we need some function that can take our numbers, have a look. It's something which can take these big numbers and turn them all into numbers between 0 and 1. And it so happens that we have exactly the right function. It's called the sigmoid function. So the sigmoid function looks like this. If you pass in a really small number, you get a number very close to 0. If you pass in a big number, you get a number very close to 1. It never gets past 1, and it never goes smaller than 0. And then it's kind of got this smooth curve between. And in the middle, it looks a lot like the y equals x line. This is the definition of the sigmoid function. It's 1 over 1 plus e to the minus x. What is exp? Exp is just e to the power of something. So if we look at e, it's just a number like pi. It's just a number that has a particular value, right? So if we go e squared, and we look at it's going to be a tensor. Use PyTorch. Make it a float. There we go. Okay, and you can see that these are the same number. So that's what torch.exp means. Okay, so for me, when I see these kinds of interesting functions, I don't worry too much about the definition. What I care about is the shape. Right? So you can have a play around with graphing calculators or whatever to kind of see why it is that you end up with this shape from this particular equation. But for me, I just never think about that. It never really matters to me. What's important is this sigmoid shape, which is what we want. It's something that squashes every number to be between 0 and 1. So we can change MNIST loss to be exactly the same as it was before, but first we can make everything into sigmoid first, and then use torch.where. So that is a loss function that has all the properties we want. It's something which is going to not have any of those nasty 0 gradients, and we've ensured that the input to the where is between 0 and 1. So the reason we did this is because our accuracy was kind of what we really care about is a good accuracy. We can't use it to get our gradients just to create our step to improve our parameters. So we can change our accuracy to another function that is similar in terms of it's better when the accuracy is better, but it also does not have these 0 gradients. And so you can see now why we have a metric and a loss. The metric is the thing we actually care about. The loss is the thing that's similar to what we care about, but has a nicely behaved gradient. Sometimes the thing you care about, your metric, does have a nicely defined gradient, and you can use it directly as a loss. For example, we often use mean squared error, but for classification, unfortunately not. So we need to now use this to update the parameters. And so there's a couple of ways we could do this. One would be to loop through every image, calculate a prediction for that image, and then calculate a loss, and then do a step, and then step the parameters, and then do that again for the next image, and the next image, and the next image. That's going to be really slow because we're doing a single step for a single image. So that would mean an epoch would take quite a while. We could go much faster by doing every single image in the data set. So a big matrix multiplication, it can all be parallelized on the GPU. And then we could then do a step based on the gradients looking at the entire data set. But now that's going to be like a lot of work to just update the weights once. And remember, sometimes our data sets have millions or tens of millions of items. So that's probably a bad idea too. So why not compromise? Let's grab a few data items at a time to calculate our loss and our step. If we grab a few data items at a time, those few data items are called a mini batch. And a mini batch just means a few pieces of data. And so the size of your mini batch is called, not surprisingly, the batch size. Right? So the bigger the batch size, the closer you get to the full size of your data set, the longer it's going to take to calculate a single set of losses, a single step. But the more accurate it's going to be like the gradients are going to be much closer to the true data set gradients. And then the smaller the batch size, the faster each step we'll be able to do, but those steps will represent a smaller number of items, and so they won't be such an accurate approximation of the real gradient of the whole data set.
Is there a reason the mean of the loss is calculated over, say, doing a median, since the median is less prone to getting influenced by outliers? In the example you gave, if the third point, which was wrongly predicted, is an outlier, then the derivative would push the function away while doing SGD, and a median could be better in that case.
Honestly, I've never tried using a median. The problem with a median is it ends up really only caring about one number, which is the number in the middle. So it could end up really pretty much ignoring all of the things at each end. In fact, all it really cares about is the order of things. So my guess is that you would end up with something that is only good at predicting one thing in the middle. But I haven't tried it. It'd be interesting to see. Well, I guess the other thing that would happen with a median is you would have a lot of zero gradients, I think, because it's picking the thing in the middle, and you could, change your values, and the thing in the middle might, well, it wouldn't be zero gradients, but bumpy gradients. The thing in the middle would suddenly jump to being a different item. So it might not behave very well. That's my guess. You should try it. Okay, so how do we ask for a few items at a time? It turns out that PyTorch and fastai provide something to do that for you. You can pass in any data set to this class called DataLoader, and it will grab a few items from that data set at a time. You can ask for how many by asking for a batch size. And then you can, as you can see, it will grab a few items at a time until it's grabbed all of them. So here I'm saying let's create a collection that just contains all the numbers from 0 to 14. Let's pass that into a data loader with a batch size of 5. And then that's going to be something, it's called an iterator in Python. It's something that you can ask for one more thing from an iterator. If you pass an iterator to list in Python, it returns all of the things from the iterator. So here are my 3 mini batches, and you'll see here all the numbers from 0 to 15 appear. They appear in a random order, and they appear 5 at a time. They appear in random order because shuffle equals true. So normally in the training set, we ask for things to be shuffled. So it gives us a little bit more randomization. More randomization is good because it makes it harder for it to kind of learn what the data set looks like. So that's what a data loader, that's how a data loader is created. Now, remember though that our data sets actually return tuples. And here I've just got single ints. So let's actually create a tuple. So if we enumerate all the letters of English, then that means that returns 0A, 1B, 2C, etc. Let's make that our data set. So if we pass that to a data loader with a batch size of 6, then as you can see, it returns tuples containing 6 of the first things and the associated 6 of the second things. So this is like our independent variable, and this is like our dependent variable. Okay, and so and then at the end, the batch size won't necessarily exactly divide nicely into the full size of the data set. You might end up with a smaller batch. So basically then we already have a data set, remember? And so we could pass it to a data loader, and then we can basically say this. An iterator in Python is something that you can actually loop through. So when we say for in data loader, it's going to return a tuple. We can destructure it into the first bit and the second bit. And so that's going to be our x and y. We can calculate our predictions. We can calculate our loss from the predictions and the targets. We can ask it to calculate our gradients. And then we can update our parameters, just like we did in our toy SGD example for the quadratic equation. So let's reinitialize our weights and bias with the same 2 lines of code before. Let's create the data loader, this time from our actual MNIST dataset, and create a nice big batch size so we do plenty of work each time. And just to take a look, let's just grab the first thing from the data loader. First is a fastai function, which just grabs the first thing from an iterator. It's useful to look at, a kind of an arbitrary mini batch. So here is the shape. We're going to have the first mini batch is 256 rows of 784 long. That's 28 by 28. So 256 flattened out images and 256 labels that are 1 long, because that's just the number 0 or the number 1, depending on whether it's a 3 or a 7. Do the same for the validation set. So here's our validation data loader. And so let's grab a batch here, testing, pass it into, well, why do we do that? We should, look. Yeah, I guess, yeah, actually for our testing, I'm going to just manually grab the first 4 things just so that we can make sure everything lines up. So let's grab just the first 4 things. We'll call that a batch. Pass it into that linear function we created earlier. So remember, linear was just x batch at weights matrix multiply plus bias. And so that's going to give us 4 results. That's a prediction for each of those 4 images. And so then we can calculate the loss using that loss function we just used. And let's just grab the first 4 items of the training set. And there's the loss. Okay. And so now we can calculate the gradients. And so the gradients are 784 by 1. So in other words, it's a column where every weight has a gradient. It's what's the change in loss for a small change in that parameter. And then the bias has a gradient that's a single number because the bias is just a single number. So we can take those 3 steps and put it in a function. So if this is calculate gradient, you pass it an x batch, a y batch, and some model, then it's going to calculate the predictions, calculate the loss, and do the backward step. And here we see calculate gradient. And so we can get the, just to take a look, the mean of the weights gradient and the bias gradient. And there it is. If I call it a second time, and look, notice I have not done any step here. This is exactly the same parameters. I get a different value. That's a concern. You would expect to get the same gradient every time you called it with the same data. Why have the gradients changed? That's because loss.backward does not just calculate the gradients. It calculates the gradients and adds them to the existing gradients, the things in the .grad attribute. The reasons for that we'll come to later, but for now the thing to know is just it does that. So actually what we need to do is to call grad.0 underscore. So .0 returns a tensor containing zeros. And remember, underscore does it in place. So that updates the weights.grad attribute, which is a tensor, to contain zeros. So now if I do that and call it again, I will get exactly the same number. So here is how you train One Epoch with SGD. Loop through the data loader, grabbing the X batch and the Y batch, calculate the gradient, prediction, loss, backward. Go through each of the parameters, and we're going to be passing those in. So there's going to be the 768 weights and the 1 bias. And then for each of those, update the parameter to go minus equals gradient times learning rate. That's our gradient descent step. And then 0 it out for the next time around the loop. I'm not just saying p minus equals, I'm saying p.data minus equals. And the reason for that is that, remember, PyTorch keeps track of all of the calculations we do so that it can calculate the gradient. Well, I don't want it calculating the gradient of my gradient descent step. That's like not part of the model, right? So .data is a special attribute in PyTorch where if you write to it, it tells PyTorch not to update the gradients using that calculation. So this is your most basic standard SGD, stochastic gradient descent loop. So now we can answer that earlier question. The difference between stochastic gradient descent and gradient descent is that gradient descent does not have this here that loops through each mini batch. For gradient descent, it does it on the whole data set each time around. So train epoch for gradient descent would simply not have the for loop at all, but instead it would calculate the gradient for the whole data set and update the parameters based on the whole data set, which we never really do in practice. We always use mini batches of various sizes. Okay, so we can take the function we had before, where we compared the predictions to whether that, well, we used to be comparing the predictions to whether they were greater or less than 0, right? But now that we're doing the sigmoid, remember the sigmoid will squish everything between 0 and 1. So now we should compare the predictions to whether they're greater than 0.5 or not. If they're greater than 0.5, just to look back at our sigmoid function. So 0, what used to be 0 is now on the sigmoid is 0.5. Okay, so we need just to make that slight change to our measure of accuracy. So to calculate the accuracy for some X batch and some Y batch, this is actually, assume this is actually the predictions. Then we take the sigmoid of the predictions, we compare them to 0.5 to tell us whether it's a 3 or not. We check what the actual target was to see which ones are correct. And then we take the mean of those after converting the Booleans to floats. So we can check that. Accuracy, let's take our batch, put it through our simple linear model, compare it to the 4 items of the training set, and there's the accuracy. So if we do that for every batch in the validation set, then we can loop through with a list comprehension every batch in the validation set, get the accuracy based on some model, stack those all up together so that this is a list, right? So if we want to turn that list into a tensor, where the items of the list of the tensor are the items of the list, that's what stack does. So we can stack up all those, take the mean, convert it to a standard Python scalar by calling .item, round it to 4 decimal places just for display, and so here is our validation set accuracy. As you would expect, it's about 50% because it's random. So we can now train for one epoch. So we can say, remember train epoch needed the parameters. So our parameters in this case are the weights tensor and the bias tensor. So train one epoch using the linear 1 model with a learning rate of 1 with these 2 parameters, and then validate. And look at that! Our accuracy is now 68.8%. So we've trained an epoch. So let's just repeat that 20 times. Train and validate. And you can see the accuracy goes up and up and up and up and up to about 97%. So that's cool. We've built an SGD optimizer of a simple linear function that is getting about 97% on our simplified MNIST, where there's just the 3s and the 7s. So a lot of steps there. Let's simplify this through some refactoring. So the kind of simple refactoring we're going to do, well, we're going to do a couple, but the basic idea is we're going to create something called an optimizer class. The first thing we'll do is we'll get rid of the linear 1 function. So remember the linear 1 function does x at w plus b. There's actually a class in PyTorch that does that equation for us, so we may as well use it. It's called nn.linear. And nn.linear does 2 things. It does that function for us, and it also initializes the parameters for us. So we don't have to do weights and bias init params anymore. We just create an nn.linear class, and that's going to create a matrix of size 28 by 28, 1, and a bias of size 1. It will set requires greater equals true for us. It's all going to be encapsulated in this class, and then when I call that as a function, it's going to do my x at w plus b. So to see the parameters in it, we would expect it to contain 784 weights and one bias. We can just call .parameters, and we can destructure it to w, b, and see, yep, it is 784 and 1 for the weights and bias. So that's cool. So this is just, it could be an interesting exercise for you to create this class yourself from scratch. You should be able to at this point, so that you can confirm that you can recreate something that behaves exactly like nn.linear. So now that we've got this object which contains our parameters in a parameters method, we could now create an optimizer. So for our optimizer, we're going to pass it the parameters to optimize and a learning rate. We'll store them away, and we'll have something called step, which goes through each parameter and does that thing we just saw. p.data minus equals p.grad times learning rate. And it's also going to have something called zero grad, which goes through each parameter and zeroes it out, or we could even just set it to none. So that's the thing we're going to call basic optimizer. So those are exactly the same lines of code we've already seen, wrapped up into a class. So we can now create an optimizer, passing in the parameters of the linear model for these, and our learning rate. And so now our training loop is loop through each mini batch in the data loader, calculate the gradient, opt.step, opt.zeroGrad. That's it. Validation function doesn't have to change. And so let's put our training loop into a function that's going to loop through a bunch of epochs, call train epoch, print, validate epoch, and then run it. And it's the same. We're getting a slightly different result here, but it's much the same idea. Okay. So that's cool, right? We've now refactoring using, creating our own optimizer and using faster PyTorch's built-in nn.linear class. And by the way, we don't actually need to use our own basic optim. Not surprisingly, PyTorch comes with something which does exactly this. And not surprisingly, it's called SGD. So, and actually this SGD is provided by fastai. Fastai and PyTorch provide some overlapping functionality. They work much the same way. So you can pass to SGD your parameters and your learning rate just like basic optim, okay? And train it and get the same result. So as you can see, these classes that are in fastai and PyTorch are not mysterious. They're just pretty, thin wrappers around functionality that we've now written ourselves. So there's quite a few steps there. And if you haven't done gradient descent before, then there's a lot of unpacking to do. So this lesson is kind of the key lesson. It's the one where, we should, really take a stop and a deep breath at this point and make sure you're comfortable. What's a data set? What's a data loader? What's nn.linear? What's SGD? And if if any or all of those don't make sense, go back to where we defined it from scratch using Python code. Well, the data loader we didn't define from scratch, but the functionality is not particularly interesting. You could certainly create your own from scratch if you wanted to. That would be another pretty good exercise. Let's refactor some more. fastai has a DataLoaders class, which is, as we've mentioned before, is a tiny class that just, you pass it a bunch of data loaders and it just stores them away as a .train and a .valid. Even though it's a tiny class, it's super handy because with that we now have a single object that knows all the data we have, and so it can make sure that your training data loader is shuffled and your validation loader isn't shuffled, make sure everything works properly. So that's what the data loaders class is. You can pass in the training and valid data loader. And then the next thing we have in fastai is the learner class. And the learner class is something where we're going to pass in our data loaders. We're going to pass in our model. We're going to pass in our optimization function. We're going to pass in our loss function. We're going to pass in our metrics. So all the stuff we've just done manually, that's all Learner does, is it's just going to do that for us. So it's just going to call this train model and this train epoch. It's just, you know, it's inside Learner. So now if we go learn.fit, you can see, again, it's doing the same thing, getting the same result. And it's got some nice functionality. It's printing it out into a pretty table for us, and it's showing us the losses and the accuracy and how long it takes. But there's nothing magic, right? You've been able to do exactly the same thing by hand using Python and PyTorch. Okay, so these abstractions are here to like let you write less code and to save some time and to save some cognitive overhead, but they're not doing anything you can't do yourself. And that's important, right? Because if they're doing things you can't do yourself, then you can't customize them, you can't debug them, you know, you can't profile them. So we want to make sure that the stuff we're using is stuff that we understand what it's doing. So this is just a linear function, which is not great. We want a neural network. So how do we turn this into a neural network? Well, remember, this is a linear function, x at w plus b. To turn it into a neural network, we have two linear functions, exactly the same, but with different weights and different biases. And in between, this magic line of code, which takes the result of our first linear function and then does a max between that and 0. So a max of res and 0 is going to take any negative numbers and turn them into zeros. So we're going to do a linear function. We're going to replace the negatives with 0, and then we're going to take that and put it through another linear function. That, believe it or not, is a neural net. So W1 and W2 are weight tensors, B1 and B2 are bias tensors, just like before, so we can initialize them just like before. And we could now call exactly the same training code that we did before for all these. So res.max 0 is called a rectified linear unit, which you will always see referred to as ReLU. And so here is, and in PyTorch, it already has this function. It's called f.ReLU. And so if we plot it, you can see it's, as you'd expect, it's 0 for all negative numbers, and then it's y equals x for positive numbers. So, you know, here's some jargon. Rectified linear unit sounds scary, sounds complicated, but it's actually this incredibly tiny line of code, this incredibly simple function. And this happens a lot in deep learning. Things that sound complicated and sophisticated and impressive turn out to be normally super simple, frankly, at least once you know what it is. So why do we do linear layer, ReLU, linear layer? Well, if we got rid of the middle ReLU and just went linear layer, then you could rewrite that as a single linear layer when you multiply things and add, and then multiply things and add. And you can just change the coefficients and make it into a single multiply and then add. So no matter how many linear layers we stack on top of each other, we can never make anything more kind of effective than a simple linear model. But if you put a non-linearity between the linear layers, then actually you have the opposite. This is now where something called the universal approximation theorem holds, which is that if the size of the weight and bias matrices are big enough, this can actually approximate any arbitrary function, including the function of how do I recognize 3s from 7s, or whatever. So that's kind of amazing, right? This tiny thing is actually a universal function approximator. As long as you have W1, B1, W2, and B2 have the right numbers. And we know how to make them the right numbers you use SGD. Could take a very long time, could take a lot of memory, but the basic idea is that there is some solution to any computable problem. And this is one of the biggest challenges a lot of beginners have to deep learning, is that there's nothing else to it. Like there's often this like, okay, how do I make a neural net? Oh, that is the neural net. Well, how do I do deep learning training with SGD? There's things to like make it train a bit faster. There's, things to mean you need a few less parameters. But everything from here is just performance tweaks, honestly, right? So this is, this is the key understanding of training a neural network. Okay, we can simplify things a bit more. We already know that we can use nn.linear to replace the weight and bias, so let's do that for both of the linear layers. And then since we're simply taking the result of one function and passing it into the next, and take the result of that function, pass it to the next, and so forth, and then return the end. This is called function composition. Function composition is when you just take the result of one function, pass it to a new one, take a result of one function, pass it to a new one. And so every pretty much neural network is just doing function composition of linear layers, and these are called activation functions or non-linearities. So PyTorch provides something to do function composition for us, and it's called nn.sequential. So it's going to do a linear layer, pass the result to a ReLU, pass the result to a linear layer. You'll see here I'm not using f.ReLU, I'm using nn.ReLU. This is identical, returns exactly the same thing, but this is a class rather than a function. Yes, Rachel?
By using the non-linearity, won't using a function that makes all negative outputs 0 make many of the gradients in the network 0 and stop the learning process due to many 0 gradients?
Well, that's a fantastic question. And the answer is yes, it does. But there won't be 0 for every image. And remember, the mini batches are shuffled. So even if it's 0 for every image in one mini batch, it won't be for the next mini batch, and it won't be the next time around we go for another epoch. So yes, it can create zeros. And if the neural net ends up with a set of parameters such that lots and lots of inputs end up as zeros, you can end up with whole mini batches that are 0. And you can end up in a situation where some of the neurons remain inactive. Inactive means they're 0. They're basically dead units. And this is a huge problem. It basically means you're wasting computation. So there's a few tricks to avoid that, which we'll be learning about a lot. One simple trick is to not make this thing flat here, but just make it a less steep line. That's called a leaky ReLU, leaky rectified linear unit. And they help a bit. As we'll learn though, even better is to make sure that we just kind of initialize to sensible initial values that are not too big and not too small, and step by sensible amounts that are particularly not too big. And generally, if we do that, we can keep things in the zone where they're positive most of the time. But we are going to learn about how to actually analyze inside a network and find out how many dead units we have, how many of these zeros we have, because as you point out, they are bad news. They don't do any work. And they'll continue to not do any work if enough of the inputs end up being 0. Okay, so now that we've got a neural net, we can use exactly the same learner we had before, but this time we'll pass in the simple net instead of the linear one. Everything else is the same. And we can call fit, just like before. And generally, as your models get deeper, so here we've gone from one layer 2, and I'm only counting the parameterized layers as layers. You could say it's 3. I'm just going to call it 2. There's 2 trainable layers. So I've gone from 1 layer to 2. I've dropped my learning rate from 1 to 0.1 because the deeper models, tend to be kind of bumpier, less nicely behaved. So often you need to use lower learning rates. And so we train it for a while, okay? And we can actually find out what that training looks like by looking inside our learner, and there's an attribute we create for you called recorder. And that's going to record, everything that appears in this table, basically. These 3 things, the training loss, the validation loss, and the accuracy, or any metrics. So recorder.values contains that kind of table of results. And so item number 2 of each row will be the accuracy. And so the capital L class, which I'm using here, has a nice little method called itemGot that will get the second item from every row, and then I can plot that to see how the training went, and I can get the final accuracy like so by grabbing the last row of the table and grabbing the second index 2, 0, 1, 2, and my final accuracy, not bad, 98.3%. So this is pretty amazing. We now have a function that can solve any problem to any level of accuracy if we can find the right parameters. And we have a way to find hopefully the best, or at least a very good set of parameters for any function. So this is kind of the magic. Yes, Rachel.
How could we use what we're learning here to get an idea of what the network is learning along the way, like Zeiler and Fergus did, more or less?
We will look at that later. Not in the full detail of their paper, but basically you can look in the dot parameters to see the values of those parameters. And at this point, why don't you try it yourself, right? You've actually got now the parameters. So if you want to grab the model, you can actually see learn.model. So we can look inside learn.model to see the actual model that we just trained. And you can see it's got the 3 things in it, the linear, the ReLU, the linear. And what I kind of like to do is to put that into a variable, make it a bit easy to work with. And you can grab one layer by indexing in. You can look at the parameters. And that just gives me something called a generator. It's something that will give me a list of the parameters when I ask for them. So I can just go weight, bias equals to destructure them. And so the weight is 30 by 784 because that's what I asked for. So one of the things to note here is that to create a neural net, so something with more than one layer, I actually have 30 outputs, not just one, right? So I'm kind of generating lots of, you can think of it as generating lots of features. So it's kind of like 30 different linear models here. And then I combine those 30 back into one. So you could look at one of those by having a look at here. So there's the numbers in the first row. We could reshape that. Into the original shape of the images. And we could even have a look. And there it is, right? So you can see this is something, so this is cool, right? We can actually see here, we've got something which is kind of learning to find things at the top and the bottom and the middle. And so we could look at the second one. Okay, no idea what that's showing. And so some of them are kind of, I've probably got far more than I need, which is why they're not that obvious. But you can see, yeah, here's another thing that's looking pretty similar. Here's something that's kind of looking for this little bit in the middle. So yeah, this is the basic idea. To understand the features that are not the first layer, but later layers, you have to be a bit more sophisticated. But yeah, to see the first layer ones, you can just plot them. Okay, so then, just to compare, we could use the full FastAI toolkit. So grab our data loaders by using data loaders from folder, as we've done before, and create a CNN learner and a ResNet, and fit it for a single epoch. And whoa, 99.7, right? So we did 40 epochs and got 98.3. As I said, using all the tricks, you can really speed things up and make things a lot better. And so by the end of this course, or at least both parts of this course, you'll be able to, from scratch, get this 99.7 in a single epoch. All right, so jargon. So jargon, just to remind us, ReLU, function that returns 0 for negatives, mini batch, a few inputs and labels, which optionally are randomly selected. The forward pass is the bit where we calculate the predictions. The loss is the function that we're going to take the derivative of. And then the gradient is the derivative of the loss with respect to each parameter. The backward pass is when we calculate those gradients. Gradient descent is that full thing of taking a step in the direction opposite to the gradients after calculating the loss. And then the learning rate is the size of the step that we take. Other things to know, perhaps the two most important pieces of jargon are all of the numbers that are in a neural network. The numbers that we're learning are called parameters. And then the numbers that we're calculating, so every ReLU that's calculated, every matrix multiplication element that's calculated, they're called activations. So activations and parameters are all of the numbers in the neural net. And so be very careful when I say from here on in these lessons activations or parameters, you got to make sure you know what those mean, because that's the entire, basically almost the entire set of numbers that exist inside a neural net. So activations are calculated, parameters are learned. We're doing this stuff with tensors, and tensors are just regularly shaped arrays. Rank 0 tensors we call scalars, rank 1 tensors we call vectors, rank 2 tensors we call matrices, and we continue on to rank 3 tensors, rank 4 tensors, and so forth. And rank 5 tensors are very common in deep learning, so don't be scared of going up to higher numbers of dimensions. Okay, so let's have a break. Oh, we've got a question. Okay.
Is there a rule of thumb for what non-linearity to choose, given that there are many?
Yeah, there are many non-linearities to choose from, and it doesn't generally matter very much which you choose. So just use ReLU or leaky ReLU, or yeah, whatever. Any one should work fine. Later on, we'll look at the minor differences between them, but it's not so much something that you pick on a per problem. It's more like some take a little bit longer and a little bit more accurate, and some are a bit faster and a little bit less accurate. That's a good question. Okay, so before you move on, it's really important that you finish the questionnaire for this chapter, because there's a whole lot of concepts that we've just done. So, try to go through the questionnaire, go back and relook at the notebook, and please run the code, do the experiments, and make sure it makes sense. All right, let's have a 7-minute break. See you back here in 7 minutes' time. Okay, welcome back. So now that we know how to create and train a neural net, let's cycle back and look deeper at some applications. And so we're going to try to kind of interpolate in. From one end, we've done the kind of from scratch version. And at the other end, we've done the kind of 4 lines of code version. And we're going to gradually nibble at each end until we find ourselves in the middle, and we've touched on all of it. So let's go back up to the kind of the 4 lines of code version and delve a little deeper. So let's go back to pets. And let's think though about like, how do you actually, start with a new data set and figure out how to use it? So the data sets we provide, it's easy enough to untar them. You just say untar, that'll download it and untar it. If it's a data set that you're getting, you can just use the terminal or raw Python or whatever. So let's assume we have a path that's pointing at something. So initially you don't know what that something is. So we can start by doing ls to have a look and see what's inside there. So the pets dataset that we saw in lesson 1 contains 3 things: annotations, images, and models. And you'll see we have this little trick here where we say path.basePath equals, and then the path to our data. And that just does a little simple thing where when we print it out, it just doesn't show us, it just shows us relative to this path, which is a bit convenient. So if you go and have a look at the README for the original pets dataset, it tells you what these images and annotations folders are. And not surprisingly, the images path, so if we go path/images, that's how we use pathlib to grab a subdirectory, and then ls, we can see here are the names, the paths to the images. As it mentions here, most functions and methods in fastai which return a collection don't return a Python list, but they return a capital L. And a capital L, as we briefly mentioned, is basically an enhanced list. One of the enhancements is the way it prints. The representation of it starts by showing you how many items there are in the list, in the collection. So there's 7,394 images. And if there's more than 10 things, it truncates it and just says ... to avoid filling up your screen. So there's a couple of little conveniences there. And so we can see from this output that the file name, as we mentioned in lesson 1, if the first letter is a capital, it means it's a cat. And if the first letter is lowercase, it means it's a dog. But this time we're going to do something a bit more complex, well, a lot more complex, which is figure out what breed it is. And so you can see the breed is kind of everything up to, after the, in the file name, it's everything up to the last underscore, and before this number is the breed. So we want to label everything with its breed. So we're going to take advantage of this structure. So the way I would do this is to use a regular expression. A regular expression is something that looks at a string and basically lets you kind of pull it apart into its pieces in a very flexible way. It's this kind of simple little language for doing that. If you haven't used regular expressions before, please Google regular expression tutorial now and look. It's going to be like one of the most useful tools you'll come across in your life. I use them almost every day. I won't go to details about how to use them since there's so many great tutorials, and there's also a lot of great like exercises. You know, there's regex is short for regular expression. There's regex crosswords. There's regex Q&A. There's all kinds of cool regex things. A lot of people like me love this tool. In order to
there's also a regex lesson in the fastai NLP course. Maybe even 2 regex lessons.
Oh yeah. I'm sorry for forgetting about the fastai NLP course. What an excellent resource that is. So regular expressions are a bit hard to get right the first time. So the best thing to do is to get a sample string. So a good way to do that would be to just grab one of the file names. So let's pop it in fname. And then you can experiment with regular expressions. So RE is the regular expression module in Python. And find all will just grab all the parts of a regular expression that have parentheses around them. So this regular expression, and R is a special kind of string in Python, which basically says don't treat backslash as special. Because normally in Python, like \n means a new line. So here's a string, which I'm going to capture any letter one or more times, followed by an underscore, followed by a digit one or more times, followed by anything. I probably should have used \dot, but that's fine. Followed by the letters JPG, followed by the end of the string. And so if I call that regular expression against my file name's name, oh, looks good, right? So we kind of check it out. So now that seems to work. We can create a data block where the independent variables are images, the dependent variables are categories. Just like before, get items is going to be get image files. We're going to split it randomly as per usual. And then we're going to get the label by calling regexLabeler, which is a just a handy little fastai class which labels things with a regular expression. We can't call the regular expression, this particular regular expression, directly on the pathlib path object. We actually want to call it on the name attribute. And fastai has a nice little function called using attribute, which takes this function and changes it to a function which will be passed this attribute. So it's going to be using regexLabeler on the name attribute. And then from that data block, we can create the data loaders as usual. There's two interesting lines here, resize and org transforms. Org transforms we have seen before in Notebook 2 in the section called data augmentation. And so org transforms was the thing which can zoom in and zoom out and warp and rotate and change contrast and change brightness and so forth and flip to kind of give us almost, it's like giving us more data being generated synthetically from the data we already have. And we also learned about random resize crop, which is a kind of a really cool way of getting ensuring you get square images at the same time that you're augmenting the data. Here we have a resize to a really large image, by deep learning standards. 460 by 460 is a really large image. And then we're using org transforms with a size, so that's actually going to use random resize crop to a smaller size. Why are we doing that? This particular combination of two steps does something which I think is unique to fastai, which we call presizing. And the best way is, I will show you this beautiful example of some PowerPoint wizardry that I'm so excited about to show how presizing works. What presizing does is that first step where we say resize to 460 by 460 is it grabs a square and it grabs it randomly. If it's a kind of landscape orientation photo, it'll grab it randomly, so it'll take the whole height and randomly grab somewhere from along the side. If it's a portrait orientation, then it'll grab it, take the full width and grab a random bit from top to bottom. So then we take this area here, and here it is, right? And so that's what the first resize does. And then the second org transforms bit will grab a random warped crop, possibly rotated, from in here, and we'll turn that into a square. And So it does, so there's two steps. It's first of all, resize to a square that's big. And then the second step is do a kind of rotation and warping and zooming stage to something smaller. In this case, 224 by 224. Because this first step creates something that's square, and always is the same size, the second step can happen on the GPU. And because normally things like rotating and image warping actually pretty slow. Also, normally doing a zoom and a rotate and a warp actually is really destructive to the image, because each one of those things requires an interpolation step, which it's not just slow, it actually makes the image really quite low quality. So we do it in a very special way in FastAI. I think it's unique, where we do all of these kind of coordinate transforms, like rotations and warps and zooms and so forth, not on the actual pixels, but instead we kind of keep track of the changing coordinate values in a non-lossy way, so the full floating point value. And then once at the very end, we then do the interpolation. The result's quite striking. Here is what the difference looks like. Hopefully you can see this on the video. On the left is our pre-sizing approach, and on the right is the standard approach that other libraries use. And you can see that the one on the right is a lot less nicely focused, and it also has like weird things, like this should be grass here, but it's actually got its kind of bum sticking way out. This has a little bit of weird distortions. This has got loads of weird distortions. So you can see the pre-sized version really ends up way, way better. And I think we have a question, Rachel.
Are the blocks in the data block an ordered list? Do they specify the input and output structures respectively? Are there always two blocks, or can there be more than two? For example, if you wanted a segmentation model, would the second block be something about segmentation?
So yeah, this is an ordered list. So the first item says I want to create an image, and then the second item says I want to create a category. So that's my independent and dependent variable. You can have one thing here, you can have three things here, you can have any amount of things here you want. Obviously, the vast majority of the time it'll be two. Normally there's an independent variable and a dependent variable. We'll be seeing this in more detail later, although if you go back to the earlier lesson when we introduced data blocks, I do have a picture kind of showing how these pieces fit together. So after you've put together your data block, created your data loaders, you want to make sure it's working correctly. So the obvious thing to do for a computer vision data block is show batch. And show batch will show you the items, and you can kind of just make sure they look sensible, that it looks like the labels are reasonable. If you add unique equals true, then it's going to show you the same image with all the different augmentations. This is a good way to make sure your augmentations work. If you make a mistake in your data block, so in this example, there's no resize. So the different images are going to be different sizes, so it will be impossible to collate them into a batch. So if you call .summary, this is a really neat thing, which will go through and tell you everything that's happening. So I'm collecting the items, how many did I find, what happened when I split them, what are the different variables, independent and dependent variables I'm creating. Let's try and create one of these. Here's each step. Create my image, create categorize. Here's what the first thing gave me, an American Bulldog. Here's the final sample, is this image, this size, this category. And then eventually it says, uh-oh, it's not possible to collate your items. I tried to collate the 0 index members of your tuple. So in other words, that's the independent variable. And I got, this was size 500 by 375. This was 375 by 500. Oh, I can't collate these into a tensor because they're different sizes. So this is a super great debugging tool for debugging your data blocks.
I have a question. How does the item transforms pre-size work if the resize is smaller than the image? Is a whole width or height still taken, or is it just a random crop with the resize value?
So if you remember back to lesson 2, we looked at the different ways of creating these things. You can use squish, you can use pad, or you can use crop. So if your image is smaller than the pre-size value, then squish will really be zoom. So it will just, well, stretch. It'll stretch it. And then pad and crop will do much the same thing. And so you'll just end up with a, the same, just looks like these, but it'll be a kind of lower, more pixelated, lower resolution because it's having to zoom in a little bit. Okay, so a lot of people say that you should do a hell of a lot of data cleaning before you model. We don't. We say model as soon as you can. Because remember what we found in Notebook 2, your model can teach you about the problems in your data. So as soon as I've got to a point where I have a data block that's working and I have data loaders, I'm going to build a model. And so here I'm, it also tells me how I'm going. So I'm getting 7% error. Wow, that's actually really good for a PETS model. And so at this point, now that I have a model, I can do that stuff we learned about earlier in 02, the Notebook 02, where we train our model and use it to clean the data. So we can look at the classification, the confusion matrix, top losses, the image cleaner widget, so forth. Okay. Now, one thing interesting here is in Notebook 4, we included a loss function when we created a learner. And here we don't pass in a loss function. Why is that? That's because fastai will try to automatically pick a somewhat sensible loss function for you. And so for a image classification task, it knows what loss function is the normal one to pick. And it's done it for you. But let's have a look and see what it actually did pick. So we could have a look at learn.lossfunc, and we will see it is cross entropy loss. What on earth is cross entropy loss? I'm glad you asked. Let's find out. Cross entropy loss is really much the same as the MNIST loss we created with that sigmoid and the 1- predictions and predictions. But it's a kind of extended version of that. And the extended version of that is that torch.where that we looked at in Notebook 4 only works when you have a binary outcome. In that case, it was, is it a 3 or not? But in this case, we've got which of the 37 pet breeds is it? So we want to kind of create something just like that sigmoid and torch.where, but which also works nicely for more than 2 categories. So let's see how we can do that. So first of all, let's grab a batch. Yes.
There's a question. Why do we want to build a model before cleaning the data? I would think a clean data set would help in training.
Yeah, absolutely. A clean data set helps in training. But remember, as we saw in Notebook 02, an initial model helps you clean the data set. So remember how plot top losses helped us identify mislabeled images. And the confusion matrix helped us recognize which things we were getting confused and might need, fixing. And the image classifier cleaner actually let us find things like an image that contained 2 bears rather than 1 bear and clean it up. So a model is just a fantastic way to help you zoom in on the data that matters, which things seem to have the problems, which things are most important, stuff like that. So you would go through and you'd clean it with the model helping you, and then you go back and train it again with the clean data. Thanks for that great question. Okay, so in order to understand cross-entropy loss, let's grab a batch of data, which we can use dls.oneBatch. And that's going to grab a batch from the training set. We could also go first, dls.train. And that's going to do exactly the same thing. And so then we can destructure that into the independent variable. And so the dependent variable shows us, we've got a batch size of 64, so it shows us the 64 categories. And remember, those numbers simply refer to the index into the vocab. So for example, 16 is a boxer. And so that all happens for you automatically when we say show batch, it shows us those strings. So here's our first mini batch. And so now we can view the predictions, that is the activations of the final layer of the network, by calling getPreds. And you can pass in a data loader. And a data loader can really be anything that's going to return a sequence of mini batches. So we can just pass in a list containing our mini batch as a data loader. And so that's going to get the predictions for one mini batch. So here's some predictions. Okay, so the actual predictions, if we go preds0.sum to grab the predictions for the first image and add them all up, they add up to 1. And there are 37 of them. So that makes sense, right? It's like the very first thing is, what is the probability that that is a else vocab? So the first thing is, what's the probability it's an Abyssinian cat? It's 10 to the negative 6, you see? And so forth. So it's basically like, it's not this, it's not this, it's not this. And you can look through and, oh, here, this one here, you know, obviously what it thinks it is. So how did it, you know, so we obviously want the probabilities to sum to 1, because it would be pretty weird if they didn't. It would say, you know, that the probability of being one of these things is more than 1 or less than 1, which would be extremely odd. So how do we go about creating these predictions where each one is between 0 and 1 and they all add up to 1? To do that, we use something called Softmax. Softmax is basically an extension of Sigmoid to handle more than 2 levels, 2 categories. So remember, the Sigmoid function looked like this. And we used that for our 3s versus 7s model. So what if we want 37 categories rather than 2 categories? We need 1 activation for every category. So actually, the 3s and 7s model, rather than thinking of that as an is3 model, we could actually say, oh, that has 2 categories. So let's actually create 2 activations, one representing how 3-like something is, and one representing how 7-like something is. So let's say, you know, let's just say that we have 6 MNIST digits, and these were the, can I do this? No. And this first column were the activations of my model for one activation, and the second column was for a second activation. So my final layer actually has 2 activations now. So this is like, how much like a 3 is it? And this is how much like a 7 is it? So this one is not at all like a 3, and it's slightly not like a 7. This is very much like a 3 and not much like a 7, and so forth. So we can take that model, and rather than having 1 activation for like is 3, we can have 2 activations for how much like a 3, how much like a 7. So if we take the sigmoid of that, we get 2 numbers between 0 and 1. but they don't add up to 1. So that doesn't make any sense. It can't be 0.66 chance it's a 3 and 0.56 chance it's a 7, because every digit in that data set is only one or the other. So that's not going to work. But what we could do is we could take the difference between this value and this value and say that's how likely it is to be a 3. So in other words, this one here with a high number here and a low number here is very likely to be a 3. So we could basically say in the binary case, these activations, what really matters is their relative confidence of being a 3 versus a 7. So we could calculate the difference between column 1 and column 2, or column index 0 and column index 1. Right? And here's the difference between the two columns. There's that big difference. And we could take the sigmoid of that. Right? And so this is now giving us a single number between 0 and 1. And so then, since we wanted 2 columns, we could make column index 0 the sigmoid, and column index 1 could be 1 minus that. And now, look, these all add up to 1. So here's probability of 3, probability of 7. For the second one, probability of 3, probability of 7, and so forth. So, like, that's a way that we could go from having 2 activations for every image to creating 2 probabilities, each of which is between 0 and 1, and each pair of which adds to 1. Great. How do we extend that to more than 2 columns? To extend it to more than 2 columns, we use this function, which is called Softmax. So Softmax is equal to e to the x divided by sum of e to the x. Just to show you, if I go softmax on my activations, I get 0.6025, 0.3975, 0.6025, 0.3975. I get exactly the same thing. Right? So softmax in the binary case is identical to the sigmoid that we just looked at. But in the multi-category case, we basically end up with something like this. Let's say we were doing the teddy bear, grizzly bear, brown bear. And for that, remember our neural net is going to have, the final layer will have 3 activations. So let's say it was 0.02, negative 2.49, 1.25. So to calculate softmax, I first go e to the power of each of these 3 things. So here's e to the power of 0.02, e to the power of negative 2.49, e to the power of 3.4, e to the power of 1.25. Okay. Then I add them up. So there's the sum of the exps. And then softmax will simply be 1.02 divided by 4.6. And then this one will be 0.08 divided by 4.6. And this one will be 3.49 divided by 4.6. So since each one of these represents each number divided by the sum, that means that the total is 1. Okay? And because all of these are positive, and each one is an item divided by the sum, it means all of these must be between 0 and 1. So this shows you that softmax always gives you numbers between 0 and 1, and they always add up to 1. So to do that in practice, you can just call torch.softmax, and it will give you this result of this function. So you should experiment with this in your own time. You know, write this out by hand and try putting in these numbers, right? And see how that you get back the numbers I claim you're going to get back, and make sure this makes sense to you. So one of the interesting points about softmax is, remember I told you that exp is e to the power of something. And now what that means is that e to the power of something grows very, very fast, right? So like exp of 4 is 54, exp of 8 is 2,980, right? It grows super fast. And what that means is that if you have one activation that's just a bit bigger than the others, its softmax will be a lot bigger than the others. So intuitively, the softmax function really wants to pick one class among the others, which is generally what you want, right? When you're trying to train a classifier to say, which breed is it? You kind of want it to pick one and kind of go for it, right? And so that's what softmax does. That's not what you always want. So sometimes at inference time, you want it to be a bit cautious. And so you kind of got to remember that softmax isn't always the perfect approach. But it's the default. It's what we use most of the time. And it works well in a lot of situations. So that is softmax. Now, in the binary case for the MNIST 3 versus 7s, this was how we calculated MNIST loss. We took the sigmoid, and then we did either 1 minus that or that as our loss function. Which is fine. As you saw, it worked, right? And so we could do this exactly the same thing. We can't use torch.where anymore because targets aren't just 0 or 1. Targets could be any number from 0 to 36. So we could do that by replacing the torch.where with indexing. So here's an example for the binary case. Let's say these are our targets, 0, 1, 0, 1, 1, 0. And these are our softmax activations, which we calculated before. They're just from some random numbers, just for a toy example. So one way to do, instead of doing torch.where, we could instead have a look at this. I could say, I could grab all the numbers from 0 to 5, and if I index into here with all the numbers from 0 to 5, and then my targets, 0, 1, 0, 1, 0, 1, 1, 0, then what that's going to do is it's going to pick for row 0, it'll pick 0.6. And then for row 1, it'll pick 1, so 0.49. For row 2, it'll pick 0.13. For row 4, it'll pick 1.003, and so forth. So this is a super nifty indexing expression, which you should definitely play with, right? And it's basically this trick of passing multiple things to the PyTorch indexer. The first thing says, which rows should you return? And the second thing says, for each of those rows, which column should you return? So this is returning all the rows and these columns for each one. And so this is actually identical to torch.where. So isn't that tricky? And so the nice thing is we can now use that for more than just 2 values. And so here's the fully worked out thing. So I've got my 3s column, I've got my 7s column, here's that target, here's the indexes from 0, 1, 2, 3, 4, 5. And so here's 0, 0, 0.6, 1, 1, 0.49, 0, 2, 0.13, and so forth. So yeah, this works just as well with more than 2 columns. So we can add, for doing a full MNIST, so all the digits from 0 to 9, we could have 10 columns, and we would just be indexing into the 10. So this thing we're doing, where we're going minus our activations matrix, all of the numbers from 0 to n, and then our targets, is exactly the same as something that already exists in PyTorch called f.nll-loss, as you can see. Exactly the same. Right, so again, we're kind of seeing that these things inside PyTorch and fastai are just little shortcuts for stuff we can write ourselves. NLL-loss stands for negative log likelihood. Again, sounds complex, but actually it's just this indexing expression. Rather confusingly, there's no log in it. We'll see why in a moment. So let's talk about logs. So this loss function works quite well, as we saw in the Notebook 04. It's basically this. It is exactly the same as we saw in Notebook 04, just a different way of expressing it. But we can actually make it better, because remember, the probabilities we're looking at are between 0 and 1. So they can't be smaller than 0. They can't be greater than 1. Which means that if our model is trying to decide whether to predict 0.99 or 0.999, it's going to think that those numbers are very, very close together, so it won't really care. But actually, if you think about the error, you know, if there's like 1,000 things, then this would like be 10 things are wrong, and this would be like 1 thing is wrong. So this is really like 10 times better than this. So really what we'd like to do is to transform the numbers between 0 and 1 to instead be between negative infinity and infinity. And there's a function that does exactly that, which is called logarithm. Okay, so the numbers we could have can be between 0 and 1. And as we get closer and closer to 0, it goes down to infinity. And then at 1, it's going to be 0. And we can't go above 0 because our loss function, we want to be negative. So this logarithm, in case you forgot, hopefully you vaguely remember what logarithm is from high school, but basically the definition is this. If you have some number that is y that is b to the power of a, then logarithm is defined such that a equals the logarithm of y comma b. So in other words, it tells you b to the power of what equals y. Which is not that interesting of itself, but one of the really interesting things about logarithms is this very cool relationship, which is that log of a times b equals log of a plus log of b. And we use that all the time in deep learning and machine learning because this number here, a times b, can get very, very big or very, very small. If you multiply things, a lot of small things together, you'll get a tiny number. If you multiply a lot of big things together, you'll get a huge number. It can get so big or so small that the kind of the precision in your computer's floating point gets really bad. Whereas this thing here, adding, is not going to get out of control. So we really love using logarithms, like particularly in a deep neural net where there's lots of layers. We're kind of multiplying and adding many times. So this kind of tends to come out quite nicely. So when we take the probabilities that we saw before, the things that came out of this function, and we take their logs, and we take the mean, that is called negative log likelihood. And so this ends up being kind of a really nicely behaved number because of this property of the log that we described. So if you take the softmax, and then take the log, and then pass that to an LL loss, because remember that didn't actually take the log at all, despite the name, that gives you cross entropy loss. So that leaves an obvious question of why doesn't NLL loss actually take the log? And the reason for that is that it's more convenient computationally to actually take the log back at the softmax step. So PyTorch has a function called log softmax. And so since it's actually easier to do the log at the softmax stage, it's just faster and more accurate, PyTorch assumes that you use soft log max and then pass that to NLL loss. So NLL loss does not do the log. It assumes that you've done the log beforehand. So log softmax followed by NLL loss is the definition of cross entropy loss in PyTorch. So that's our loss function. And so you can pass that some activations and some targets and get back a number. And pretty much everything in PyTorch, every one of these kinds of functions, you can either use the NN version as a class, like this, and then call that object as if it's a function, or you can just use f dot with the camel case name as a function directly. And as you can see, they're exactly the same number. People normally use the class version. In the documentation in PyTorch, you'll see it normally uses the class version. So we'll tend to use the class version as well. You'll see that it's returning a single number, and that's because it takes the mean, because a loss needs to be, as we've discussed, the mean. But if you want to see the underlying numbers before taking the mean, you can just pass in reduction equals none, and that shows you the individual cross-entropy losses before taking the mean. Okay. Great. So this is a good place to stop with our discussion of loss functions and such things. Rachel, were there any questions about this?
Why does the loss function need to be negative?
Well, I mean, I guess it doesn't, but it's we want something that the lower it is, the better. And we kind of need it to cut off somewhere. I have to think about this more during the week because I'm a bit tired. Yeah, so let me refresh my memory when I'm awake. Okay. Now, next week, well, note not for the video. Next week actually happened last week. So the thing I'm about to say is actually referring to. So next week we're going to be talking about data ethics. And I wanted to kind of segue into that by talking about how my week's gone. Because a week or two ago, I did as part of a lesson, I actually talked about the efficacy of masks, and specifically wearing masks in public. And I pointed out that the efficacy of masks seemed like it could be really high, and maybe everybody should be wearing them. And somehow I found myself as the face of a global advocacy campaign. And so if you go to masksforall.co, you will find a website talking about masks. And I've been on TV shows in South Africa and the US and England and Australia and on radio and blah, 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 talking about masks. Why is this? Well, it's because as a data scientist, I noticed that the data around masks seemed to be getting misunderstood. And it seemed that misunderstanding was costing possibly hundreds of thousands of lives. Literally in the places that were using masks, it seemed to be associated with, orders of magnitude fewer deaths. And one of the things we'll talk about next week is like, what's your role as a data scientist? And I strongly believe that it's to understand the data and then do something about it. And so nobody was talking about this. So I ended up writing an article that appeared in the Washington Post that basically called on people to really consider wearing masks, which is this article. And I was lucky. I managed to kind of get a huge team of brilliant not huge, a pretty decent sized team of brilliant volunteers who helped, kind of build this website and kind of some PR folks and stuff like that. But what became clear was, I was talking to politicians, senators, staffers, and what was becoming clear is that people weren't convinced by the science, which is fair enough, because it's hard to, when the WHO and the CDC are saying you don't need to wear a mask, and some random data scientist is saying that doesn't seem to be what the data's showing, if you've got half a brain, you would pick the WHO and the CDC, not the random data scientist. So I really felt like if I was going to be an effective advocate, I needed to sort the science out. And it, credentialism is strong. And so it wouldn't be enough for me to say it. I needed to find other people to say it. So I put together a team of 19 scientists, including, a professor of sociology, a professor of aerosol dynamics, the founder of an African movement that kind of studied preventative methods for tuberculosis, a Stanford professor who studies mask disposal and cleaning methods, a bunch of Chinese scientists who study epidemiology modeling, a UCLA professor who is one of the top infectious disease epidemiologist experts, and so forth. So like this kind of all-star team of people from all around the world. And I had never met any of these people before. So, well, no, not quite true. I knew Austin a little bit, and I knew Zeynep a little bit. I knew Lex a little bit. But on the whole, and well, Reshma, we all know she's awesome. So it was great to actually have a fastai community person there too. And so, but yeah, I kind of tried to pull together people from, as many geographies as possible and as many areas of expertise as possible. And, the kind of the global community helped me find papers about everything, about, how different materials work, about how droplets form, about epidemiology, about case studies of people infecting with and without masks, blah, blah, blah. And we ended up in the last week, basically, we wrote this paper. It contains 84 citations. We basically worked around the clock on it as a team, and it's out. And it's been sent to a number of, some of the earlier versions 3 or 4 days ago, we sent to some governments. So one of the things is in this team, I try to look for people who were, working closely with government leaders, not just that they're scientists. And so this went out to a number of government ministers. And in the last few days, I've heard that it was a very significant part of decisions by governments to change their guidelines around masks. And the fight's not over by any means. In particular, the UK is a bit of a holdout. But I'm going to be on ITV tomorrow and then BBC the next day. It's kind of required stepping out to be a lot more than just a data scientist. I've had to pull together, politicians and staffers. I've had to, hustle with the media to try and get, coverage. And, today I'm now starting to do a lot of work with unions to try to get unions to understand this. It's really a case of like saying, okay, as a data scientist and in conjunction with real scientists, we've built this really strong understanding that masks, are this simple but incredibly powerful tool that doesn't do anything unless I can effectively communicate this to decision makers. So today I was, on the phone to, one of the top union leaders in the country, explaining what this means. Basically, it turns out that in buses, in America, the air conditioning is set up so that it blows from the back to the front. And there's actually case studies in the medical literature of how people that are seated kind of downwind of an air conditioning unit in a restaurant ended up all getting sick with COVID-19. And so we can see why like bus drivers are dying because they're right in the wrong spot here and their passengers aren't wearing masks. So I kind of trying to explain this science to union leaders so that they understand that to keep the workers safe, it's not enough just for the driver to wear a mask, but all the people on the bus need to be wearing masks as well. So, all of this is basically to say, as data scientists, I think we have a responsibility to study the data and then do something about it. It's not just a research, exercise. It's not just a computation exercise. What's the point of doing things if it doesn't lead to anything? Next week we'll be talking about this a lot more, but I think, this is a really, to me, kind of interesting example of how digging into the data can lead to really amazing things happening. And in this case, I strongly believe, and a lot of people are telling me they strongly believe, that this kind of advocacy work that's come out of this data analysis is already saving lives. And so I hope this might help inspire you to take your data analysis and to take it to places that it really makes a difference. So thank you very much, and I'll see you next week.